Alright, David Can here with another question bank question in the style of the questions you find in Chapter 9a of your Hayes and Harris Math SL textbook. And this is about you finding areas of non-right angled triangles. In this question we're shown a diagram about a semicircle with center O and diameter AB. It has a radius of 2 units, and P is any point on the circumference, and we'll call angle POB angle theta. All of this information is in the diagram already. What we're going to try and do is we're going to try and find the area of the triangle OPB in terms of theta. So for part A, we want the area of this triangle. Now in general, the area of a triangle is 1/2 AB sine of angle C, where C is the angle between A and B. A and B are two of the sides of the triangle. What I know is one of the sides, but I also know a second. I know that this side also has to be 2 because OB is also a radius of the circle O. So both sides must have length 2. And then finally the angle between them is given as theta, and I can use that. So I'll find that area is equal to 1/2 times 2 for A, 2 for B, and the sine of theta for angle C. This gives me 2 sine of theta for my expression for the area of that triangle. Part B asks me to explain why the area of triangle OPA is the same as the triangle OPB. So basically these two triangles have the same area, and they expect me to explain why. Well, to explain why, first I'll try finding the area of triangle OPA, and I'll do it the same way by saying that the line OA also has units 2. I'll also need the angle between them, and since this angle and this angle must add up to 180 degrees, the angle must be 180 take theta. So to find the area of triangle 2, and I'll call it triangle 2, that's going to be 1/2 times side 1 times side 2 times the sine of the angle between them. That'll be 1/2 times 2 times 2 times the sine of 180 take theta. This will be 2 sine of 180 take theta, which is not quite the same expression as this one, but in fact they are equivalent, and we'll find out by looking at the unit circle. So we'll draw a unit circle, and we'll draw some angle theta. If this is the angle theta, then this is the angle 180 degrees take theta, working backwards from the other side of the unit circle. And what we see is that the vertical component of this line is the same. So the sine of the blue line, whether you go this way or that way, is the same. And so what we can say is that the sine of theta is equal to the sine of 180 take theta. And so therefore, the other angle's area is also, the other triangle's area is also 2 sine of theta. So we've shown that the two triangles, A1 and A2, A1 and A2, must have the same area. So for the next part, it takes us to another diagram, and it says let S be the total area of the 2 segments that are shaded in the diagram, and so that's this segment here and this little sliver of a segment here. And we want to show that the total area is equal to this expression. Now for a show that question, the rule is that you can't use this information, what you're meant to show. You have to arrive at that information. So we can't start here, we must end here. We have to start with some other relationship between these areas. And what I see is I see that the shaded areas are just the area of the half circle take away the area of the 2 triangles. So what I would say for part C is that S, the total of the shaded areas, is just going to be the area of a half circle, take away 2 areas of the triangles. Half an area of a circle is 1/2 pi r squared. Take away the area of each of the triangles, which we found to be 2 sine of theta. R in this case is 2, so this is 1/2 pi times 2 squared, take 4 sine of theta. 2 squared is 4, multiply that by half, and you get 2 pi, take 4 sine theta. And finally, to create the expression that they wanted, I'm going to factorize out a 2. I'll pull a 2 out, and I'll leave pi, take 2 sine theta. For part D, it says to find the value of theta when S is a local minimum. So basically, when is the area given minimized? And we'll try and justify that it is the minimum. So this is an optimization question. We're going to try and optimize our formula for area, S. Now we have 2 end formulas, but I think that our second to last one is more simple than the last one. So I'm going to revert in part D back to S is equal to 2 pi, take 4 sine theta. Now in this, I need to look at the limits on theta, and that'll come from the situation. In this situation, theta is allowed to be any angle along this half circle. So it can go from 0 all the way out to 180 degrees. So theta must be between 0 and 180 degrees. But there are possibilities for the locations of other minimums, and that'll come from finding when the derivative of the formula for area is equal to 0. So I'll find where the derivative of the area is equal to 0. So I need to find that derivative. The derivative of 2 pi with respect to theta is 0. That goes away. And then we have negative 4 times the derivative of sine, which is cosine. Now this is meant to be equal to 0, so we'll say 0 is equal to negative 4 cosine of theta. To solve for theta, we'll divide 4 to the other side. 0 divided by negative 4 is 0, so 0 is equal to the cosine of theta. Finally, I'll take the inverse trigonometric function and say that theta is equal to the inverse cosine of 0. Now, 0 is a length along the unit circle that we are meant to know by hand, so we won't be able to use a calculator to solve this. We'll have to go to the unit circle. So we'll draw in yet another unit circle, and we'll say the cosine of a length of 0. So basically, when along the x-axis do you have no displacement? You have that when you're all the way up here at 90 degrees. You also have it when you're all the way down at 270 degrees, but 270 degrees is outside the bounds on what theta is allowed to be, and so 270 degrees is not a solution, only 90 degrees is. So theta could be 90 degrees. What we have now are 3 possibilities for the local minimum, or any minimum, of the area. The possibilities are theta could be 0, theta could be 90 degrees, or theta could be 180 degrees. This comes from my solutions to when the derivative is 0, as well as the limits on my function. What I have to do is I have to determine which of these is the smallest, and I'll find out by plugging them into my formula for area, which was 2 pi, take 4 sine of theta. If I plug in 0, I get 2 pi, take 4 sine of 0. If I plug in 90, I get 2 pi, take 4 sine of 90. And if I plug in 180, I get 2 pi, take 4 sine of 180 degrees. Now the sine of 0 degrees, going back to the unit circle once again, if we're looking at 0 degrees, the height for 0 degrees is 0. If we look at 90 degrees, the height for 90 degrees is 1. And if we look at 180 degrees, the height for 180 degrees is 0 again. So what this gives me is 2 pi. 2 pi take 4, and 2 pi. Of these three options, the smallest is going to be 2 pi take 4, because all of them are 2 pi, but this one is 2 pi subtract 4. So 2 pi take 4 is the minimum when theta equals 90 degrees. So we found the value of theta for when s is a minimum. We've justified it by comparing it to all the possible values. The final thing we'll do is find a value for theta for which s has its greatest value. Now the nice thing is that the way you find a maximum is the same as the way you find a minimum. To find a maximum, you look at the endpoints of the function and you look at where the derivative is equal to 0. And we've done all of that already. So for part E, what we'll do is we'll just look at the values that we already had and we'll find which are the maximum. So we'll say from above, we have a max of 2 pi for the area. And it occurs when theta is equal to 0 and 180 degrees.